code has structure. A parser can read a string of characters and map it perfectly to a grammatical wireframe. But to a machine, that structure is useless until it has evaluable meaning. Parsing alone only verifies the grammar. It generates a parse tree, but those nodes are entirely empty. They contain no inherent mathematical value, no memory locations, and no data types. To bridge this gap, compilers use syntax-directed translation. This is the mechanism that performs semantic actions simultaneously during the parsing phase, injecting specific values into the rigid grammar. Compilers define these rules using two primary notations. The first is syntax-directed definitions, or SDDs. These are high-level specifications that use a table of rules and intentionally hide the underlying implementation details. The second notation is translation schemes. These operate at a lower level by embedding the exact semantic actions, the actual code, written inside brackets, directly into the grammar productions themselves. To understand how a compiler processes language and to score full marks in compiler design, you have to master how these definitions evaluate data across a parse tree. Ultimately, syntax-directed translation provides the necessary mechanism required to transform rigid, static grammatical rules into active, computable computational intent. This diagram shows a standard parse tree being populated with attributes. Attributes are the specific metadata bound to every grammar symbol. This can be a numeric value, a data type, a memory location, or intermediate code. The process begins at the bottom. Terminal symbols usually receive their initial attributes directly from the lexical analyzer. If the code contains a number, the lexer provides its raw numeric value to the leaf node. The non-terminals higher up in the tree must compute their attributes using the specific semantic rules associated with their grammar productions. The mechanical complexity of computing these rules depends entirely on the direction the data has to travel through the branches. This flow of data strictly divides all syntax-directed definitions into two architectural categories, S-attributed and L-attributed definitions. The direction these attributes move, either strictly bottom-up or passing context top-down, dictates the specific sequence the compiler must follow to resolve the tree. This parse tree maps 3 times 5 plus 4. Solid upward arrows represent synthesized attributes, computed strictly from a node's children. Values 3 and 5 bubble up to compute 15, which meets the 4, flowing upward to compute the final expression value of 19. This upland data flow is a post-order traversal. Because children are evaluated first, the entire tree can be evaluated in a single bottom-up pass. Any syntax-directed definition that relies exclusively on these synthesized attributes is called an S-attributed definition. This explicit bottom-up reliance makes S-attributed models the standard for implementation during LR parsing. Because the data flows strictly from the leaves to the root, S-attributed models guarantee a single-pass evaluation that perfectly mirrors the nuptial completion of a parser's branches. S-attributed models are fast, but they cannot pass context downwards. If you assign an integer type to a list of variables, a strictly bottom-up model cannot distribute that type information to the identifiers. This dotted parse tree maps a type declaration, like declaring variables as integers. Watch this solid arrow move down and across. This inherited attribute is computed not from a node's children, but from its parent or siblings. Compilers use L-attributed definitions, a flexible grammar permitting both synthesized and inherited attributes. But there is a restriction. An inherited attribute can only depend on its parent, or symbols explicitly to its left. This prevents cyclical paradoxes, where nodes wait for each other to resolve, ensuring the tree evaluates cleanly in a single left-to-right pass. Because of this dependency chain, the start symbol of a grammar cannot have inherited attributes, unless explicitly stated, as it has no parent or left sibling to inherit from. Inherited attributes let compilers track state. By passing context across the tree, L-attributed definitions provide the required mechanism to resolve variable types and maintain scope. Abstract dependency graphs explain the theory, but the computer has to physically implement this mathematics during bottom-up parsing. This split screen shows how memory is managed. Compilers do not keep the entire parse tree in active memory. Instead, they use a parallel structure. The parser stack on the left stores states, while the semantic stack on the right stores attribute values. Consider a Y-ACT-style reduction. E produces E plus T. When the parser recognizes the completed right side, it performs a reduction. 3 states pop off the parser stack, and simultaneously their 3 corresponding values pop off the semantic stack. The array logic accesses those popped children, adding the value from 2 positions down to the value at the top. That newly computed parent value, 19, is then pushed back onto the top of the semantic stack. This alignment between parser states and semantic values shows how bottom-up evaluation rules are implemented through physical stack operations. This diagram illustrates the relationship between the 2 grammar classes. L-attributed definitions form the comprehensive outer set, while S-attributed definitions are fully enclosed within it. Every S-attributed definition is inherently L-attributed, because an L-attributed grammar permits synthesized attributes. However, an L-attributed definition is not S-attributed if it uses a single inherited attribute. When you map these operations out, the combination of dotted parse tree lines representing syntax and solid arrows representing attribute flow forms a dependency graph. To evaluate the attributes, the compiler performs a topological sort. This establishes an ordering of the nodes guaranteeing that if attribute A depends on attribute B, B is calculated first. This table summarizes the functional differences. If the graph contains a cycle where A depends on B and B depends back on A, the topological sort fails, making the definition invalid. S-attributed models use synthesized attributes evaluated bottom-up for mathematical computation. L-attributed models incorporate inherited attributes evaluated left to right to establish contextual scope. The direction of attribute flow is the immutable blueprint that determines whether a compiler can successfully translate code into meaningful action.